Hello, welcome back. So, today in this lecture we will see major concepts of ceramic processing. As you know, the ceramic materials are different in their characteristics of bonding. So, it makes them different in properties as well as the processing. So, as you know, the ceramics are inherently different in their characteristics of bonding. So, that makes them stable at high temperature, but the same characteristic of high temperature stability makes them unsuitable to process a ceramic material by conventional routes. So, conventional routes of processing, for example, this solidification, right, is very difficult because high temperature stability means that comes from the bonding. So, you have ceramics with higher melting point, right. So, high melting point ceramics material cannot be melted easily. So, you require high temperatures. So, maintaining high temperatures in furnaces for long time for the production point of view is itself a difficult. So, it is very difficult to process these ceramic materials through conventional fabrication routes. So, the reason behind this is the very specific characteristic of ceramics, that is high temperature stability, right. But how they are manufactured? They are manufactured generally through powder processing. That means, you have a powder of the ceramic material, right, and then the ceramic powders are compacted to give a shaped component. So, for an engineering application, you need to have a ceramic component with a definite shape and a good properties. So, mostly ceramic products are manufactured through powder processing, right, that you start with powder of that material and then make it a component. So, typically ceramic processing routes involve powder synthesis step followed by the compaction step followed by the most important step, that is sintering. Today in this class, so we will learn about these very important steps in the ceramic processing, right. Particularly we will focus on the last part, sintering, because that gives large difference in the microstructure as well as the resultant properties. So, the microstructure and resultant properties differences make them suitable or unsuitable for the given tribological applications. That means, the sintering influences the microstructure results in a mechanical property variation that will lead to a different performance in the given tribological conditions. So, ceramic materials processing must be studied thoroughly, right. So, if you look at the overall chart of this ceramic processing, so first we take these powders, right, powders of the ceramic materials, and then we will mix it, right. So, we will mix it. After mixing, we will keep it in a die cavity and then close this upper and lower punch and give certain pressure that we call compaction. So, compaction generally done in a unidirectional way. So, this upper punch and lower punch are given a pressure, so that the powder, loose powder, is compacted. So, when these loose powders they are compacted, they just come in contact, nothing else will happen. So, this is just sufficient to handle this material, this powdered material in a definite shape, but the bonding is not formed, but it is very poorly bonded. So, this particular powder compact is ejected from the compaction die, and then after that we will do the sintering, that is heating this material in a controlled atmosphere and a controlled processing way, so that there happens certain metallurgical bonding between these powder particles. So, you get a ceramic component of this shape with a strong bonding between these grains of, right. So, mainly the blending compaction and sintering. There are three major steps in the processing of a ceramic component. So, powder synthesis generally done by either chemical way or a mechanical way. Important chemical synthesis methods for the powders of ceramics are chemical vapor deposition, inert gas condensation, precipitation process, and then pyrolysis or sol gel. So, we are not going into details of these all chemical synthesis routes, but considering the importance, we will just go through the mechanical synthesis route, that is by ball milling. The major synthesis of powders of ceramics is by ball milling. So, we will just see the principle of this ball milling. So, ball milling is generally done to reduce the starting particle size of the powder or to mix different powders, right. So, ball milling is done to reduce the starting powder particle size by a process called comminution. This comminution happens because of the repeated crushing of the powder particles by the balls. So, we use certain balls, right, and these balls move at a high speed in a container, right. So, in this container these balls and powders are placed and they are rotated at a particular speed. Because of this, there is a high energy collision happening, and the high shearing action between these hard balls and the powders that lead to size reduction by comminution, then as well as the grain size reduction by internal energy generation. So, this particular synthesis gives very high yield, and the procedure is very simple than any other process of any other synthesis. So, because of that, this ball milling has gained wide applicability in the industries as well as in research laboratories. So, as I told, we use the balls of certain material which always have a hardness which is more than the hardness of the ceramic powders you are mixing, right. So, you generally balls of type agate, right, or the tungsten carbide, aluminum oxide or agate or zirconium oxide balls are used for the ceramic powder synthesis. Generally for metallic powders synthesis by ball milling, we use stainless steel balls in a stainless steel vial. So, this vial for ceramics generally we go for the harder vial, that means at least the surface inside the vial is of tungsten carbide or aluminum oxide, silicon oxide like this. So, we use a combination of a vial and the balls and a particular powder material to ball material ratio generally 1:4 to 1:10 are used, and milling is done in a particular speed for a particular duration. So, in a definite environment, if you do in a uncontrolled environment, there is a chance for the oxidation to happen for a non-oxide ceramic materials, right. So, controlled atmospheres are generally preferred to prevent such type of oxidation of powders, either it is metallic or the ceramic. There is a to prevent oxidation of the powders, generally milling is done in a controlled atmosphere, controlled environments, that is inert gases, and milling is done either in a dry condition or we use the medium toluene or acetone. These are filled, this vial is filled with this, and then you get a insert this ball and the powder mixture. So, at least half of the vial volume is filled with this milling medium and the ball and powder mixture, and they are rotated. So, here is an example to show you two jar. So, they are rotated. In this rotation, planetary rotation is more efficient to reduce the particle size as well as the mix different powders of different composition. So, this planetary ball mill gives a high energy collision. So, it is usually called high energy ball mill, right. So, high energy ball mill is generally used for the ceramic powders, but the high energy ball milling has certain limitation. So, because we use the balls and vials, so there is a chance for the contamination from the balls or vial material into the powder mixture. So, and this may also result into a broad particle size distribution. right. And if you look at this, the size of the crystallite as a function of milling time. So, there is a decrease in the size of this crystallite initially. So, after obtaining certain crystallite size, there is no much difference in the crystallite size. So, generally what happens because of this high energy collisions, there is a fracture of this material, right. So, initially deformation and then fracture happens and they cold weld each other and then form a almost a spherical particle. So, a fine sized powder will become more agglomerated and then there is no much influence of prolonging the milling on the size of the particle. So, there is no much difference after certain time. So, you need to identify the lower limit below which the refinement is not possible. So, for every material there is a lower limit below which the refinement is not possible. So, for those studies which you require a size reduction to a larger extent, this becomes a major point, right. So, and you can see one example of these powders of almost nano size, right, but you can see because of the reduced particle size they tend to agglomerate each other. So, finer particle size tend to agglomerate very easily. So, there happens a certain pores happening in a interagglomerates as well. This ball milling is much useful even in industries because of its simplicity, right. So, after this ball milling, so we will go to the next stage, we will go to the next step of this processing of ceramics. So, powders they are synthesized. So, after the synthesis these powders are pressed into the desired shape and size using a hydraulic or mechanical press to obtain a compact, right. So, all these powders after keeping in a die and pressing, right, either by hydraulic or mechanical press. So, this will lead to, right, this will lead to a compact and it is named as green compact, right. So, green means it is not heated, right. So, the powders are loosely contacted with each other. The compaction without heating the powders is usually called cold pressing, or there are certain compactions where the high temperatures can also be applied. So, but cold pressing is much more useful and the pressing can be a unidirectional or a isostatic one, right. So, unidirectional compaction is much widely used. So, you can see the different steps in the unidirectional compaction. First you fill this die cavity with the powder, right, and then close this punch, upper punch. So, you have a set of upper punch, lower punch and a die, and this die has a cavity which is filled with the powder. Now, you apply the pressure. So, you can see while applying the pressure, you can see there is a shrinkage of this powder bed, right. So, after this application of the pressure, so you can eject it. So, there is a filling of the powder, initial and final positions of upper and lower punches, right, while pressing, and then this is after ejection. So, now we come to the very important step in the processing of ceramics, the sintering, right. Sintering fundamentally, sintering refers to the process of heating, right. Sintering is nothing but heating. So, fundamentally sintering refers to the process of consolidation of a porous powders to a dense solid, but you can have, by definition, sintering is a process of firing of a loosely contacted powder bed at a temperature more than half of the melting point, and the melting point is generally in absolute scale. So, because of the heating at a temperature more than the half of the melting point, there is a considerable diffusional mass transport. the diffusional mass transport leads to consolidation of this loose powder compact to a dense component, right. So, sintering refers to the process of consolidation of porous powders compact to a dense solid at a temperature usually more than the half of the melting point and is assisted by the diffusional mass transport. So, you heat it at a temperature where diffusion is possible. Because of the diffusion, the atoms move from one location to the other location. So, there is a bonding happening at the grain boundaries level. So, there is a strong metallurgical bonding happening because of this heating that leads to a dense body, right. So, you can see the loose powder particles, they are heated and you can see this white portion is nothing but the porosity, right. So, while heating actually the diffusional mass transport leads to the consolidation and leads to elimination of such a porosity, and then you have a strongly bonded grains of this ceramic compact. So, we call it as sintered ceramic. So, we understand that sintering is because of the movement of atoms that occur at high temperatures and the reduction in the surface energy associated with the particles. We will see for the liquid phase sintering, right, major characteristic of liquid phase sintering. If you have a material with a lower melting point than the powder material, right, which you want to sinter. So, this low melting point material will be melted before you reach the peak temperature for the sintering. So, at lower temperatures this liquid melt is formed. So, this liquid melt will penetrate in the solid particle mixture, and because of this penetration it goes and wets the surface of the solid particles. Based on the wettability, there is a large capillary forces, and these capillary forces bring the solid particles closer, and there is a chance for the necking, right. So, the liquid provides a brace that bonds the grains together with a faster diffusion rates. An essential requirement for the liquid phase sintering is wetting. The liquid must spread over the solid grains. So, if you see this, the contact angle is much more important in the liquid phase sintering. There is a liquid and it has interface with the vapor and the solid. The liquid must spread over the solid grains. So, contact angle is very much critical to have effective liquid phase sintering. A wetting liquid film provides a surface tension that aids densification termed as a capillary force. So, in addition, the solubility also ensures the solid can diffuse through the liquid. So, because it is diffusing through the liquid, the diffusion rates are much higher than compared to solid state sintering. So, the liquid becomes a carrier for the solid atoms in a process termed as solution and reprecipitation. So, what happens while this liquid phase sintering? So, the liquid penetrates into the solid particle gaps, the liquid penetrates into the gaps, right, and it dissolves the solid material, right, and this dissolved material will be precipitated in the other stages of the sintering. There is a certain fraction of the material which is dissolved and it is not precipitated back. So, after sintering we will find a material which is not precipitated. So, after sintering we will find a microstructure with a core and rim phases. The core phase is the retained phase and the precipitated phase is this rim phase. You see this rim phase, right, rim phase, and this is actually binder for the given material here, nickel. So, this is a nickel rich binder. So, because of the lower melting point, the liquid of the nickel penetrates, and then because of the good wettability with the ceramic particles, they are dissolved. The ceramic particles are dissolved in the liquid and forms and precipitates back. So, there is always a solution and a reprecipitation happening that will lead to a core and the rim microstructure, right. So, the amount of liquid formed is very important in achieving a proper density. So, you see this as this is amount of liquid and this is density schematically shown here. So, finally, the solution and reprecipitation which is happening in the intermediate stage results into a larger densification, right. First of all, this is soluble, the liquid dissolves the material solid and then rearrangement is happening. After that, the solution reprecipitation, then when completely the liquid is consumed, you will have only solids, right. So, that becomes solid state sintering. So, in the final stage it is nothing but a solid state sintering. So, dissolution and then resolution, rearrangement of this particle, solution reprecipitation and then again solid state sintering. So, these are the major stages in the liquid phase sintering. Let us now see the major techniques of this sintering. Conventionally, the sintering is called pressureless sintering. What do you mean by that? Sintering is possible only by heating the powder mixture, right. You do not apply any external gas or mechanical pressure. So, a powder compact is heated to a sintering temperature in a furnace without application of any pressure, right. So, and this is the most inexpensive sintering technique and this is the most widely used sintering technique. But because of only the effect of the sintering temperature, you need to give larger temperatures for the sintering to happen. That means to have a diffusion to happen to give a considerable mass flow, right, that result into the consolidation. So, for the consolidation to happen, you need to give higher temperatures in this particular conventional sintering technique. Because of the simplicity in the technique, and this pressureless sintering is widely used in industries as well. So, you can see one schematic of a continuous sintering furnace. So, where you see the powder bed will come and this is preheated and then this is subjected to the sintering and then cooling is happening and then after that component is taken back. So, there is a continuous process of preheating, sintering, cooling down and all these things. So, you need to decide the temperature and the time, right. If you heat it to a temperature lesser than the required temperature for the sintering, the densification is not complete, right. So, sometimes you need to do this type of lower temperature sintering to produce a porous ceramics, right, porous materials. Whereas, usually for the tribological applications we require dense ceramics. So, always our aim is to achieve the density as maximum as possible, right. So, fully dense ceramic components are generally preferred for the tribological applications. So, that means the temperature needed for the sintering is to be selected such that the densification happens to the larger extent. And also if you give a higher temperatures, the diffusion happens more and then you do not have a control on the sintering, and there is no need for giving such a high temperature if you get a same densification happening at a much lower temperatures, right. So, the optimum temperature is very important to get the densification easily for the ceramic powders, right. And also the time needed for the sintering is also to be selected. So, the optimum time required to sintering is to be selected. If you prolong the sintering at high temperatures, that will lead to coarsening, right. So, generally speaking, if you have a larger sized grains, the strength of the material is decreased, Hall pitch relation, right. So, if you have a finer sized grains, you have a higher strength as per the Hall-Petch relation. So, generally we do not prefer to have the coarsening happen at a larger extent. Unless it is required, we do not go for the coarsening to happen to a larger extent. So, if you give lesser time, so you do not have the the densification happening to a larger extent. So, the selection of optimum temperature and time for the sintering is much important. So, generally a cycle called sintering cycle is designed, the time and temperature. So, initially this is heated at a rate, and then you have heated to a higher temperature and then allow it for a time and then cool it, right. So, the rate of this heating and the rate of this cooling are also very important. In a conventional pressureless sintering furnaces, generally we go 2 to 10 degree per minute, right. This type of heating or cooling are possible, and the temperature required, as I told, it is at least more than half of the melting point, and melting point in absolute scale, T in absolute scale, right, melting point. So, you need, for a given material, you have to select the proper temperature and the proper time for the sintering. And because of this conventional pressureless sintering, the densification may be less. Hot pressing is one advanced sintering technique which is being used for preparing a ceramic component with high density and good mechanical properties. In this hot pressing, we apply the pressing as well as heating simultaneously. So, the high pressure and temperature synergetically allow rearrangement of particles, allow plastic flow, and facilitates faster mass transport, leading to enhanced neck growth in vacuum or inert atmospheres. So, because of this pressing, these are the powder particles, right. So, you apply the pressure at high temperatures, right. The pressure can be applied again in a unidirectionally or in all directions. In that, if you apply in all directions, it is called isostatic pressing, right. Because of the application of external pressure, you will have a compressive forces that result into a enhanced mass transport in the neck region. So, you can see lot of mass transport happening in the neck region. So, because of this increased mass transport, the diffusion rates are higher and you get a densification easily. What do you mean by that? At a temperature lesser than what you require in a conventional sintering process. Generally speaking, 100 Celsius to 150 Celsius lesser temperatures are sufficient to give a same densified body of ceramic when you compare with the conventional pressureless sintering technique. So, generally high pressures of around 20 to 40 MPa are applied at high temperatures, and the temperatures are reached at a heating rate of more than 10 degrees Celsius, usually 50 degree Celsius per minute, and you do this hot pressing for several hours, right, and the sintering atmosphere can be inert or vacuum. Generally in an argon or nitrogen atmosphere, so silicon carbide, silicon nitride or any other ceramic material. So, the driving force for the densification is increased by one order of magnitude. So, the temperature required for the sintering to happen is reduced, and generally speaking 100 to 150 degrees Celsius lesser temperatures are sufficient to produce a ceramic of a decent density, right. For the same density, the conventional sintering requires higher temperature. So, by hot pressing we can produce ceramics of high purity and high strength. Hot pressing is only suited to relatively simple shapes, right. As I told, the application of both pressure and heat simultaneously. So, there is a limitation in the mechanism of this machine. So, hard pressing is generally suited to relatively simple shapes with components usually requiring diamond grinding to achieve the finish tolerances. But if you go for a complicated shapes, the distribution of the load at high temperatures becomes difficult, right. So, generally hard pressing is preferred for the simple shapes, relatively simple shapes. So, you can see here there is upper punch and lower punch. Here you have a die, inside this there is a die, and the die is filled with the powder, right, die cavity, and then cavity is filled with the powder. So, generally these dies are made up of graphite dies, and there is a heating element in the chamber. So, you have a heating by this heating element and pressing by this mechanical pressing. So, you have the pressing and heating simultaneously happening, that leads to enhanced mass transport in the neck region, that leads to easy densification. Coming to the other technique, which is very important and very much famous nowadays, advanced sintering technique called spark plasma sintering technique. So, spark plasma sintering is generally based on the electrical spark discharge phenomenon, right, that involves the use of high current together with the low voltage pulse momentarily generating a spark plasma in the interparticle neck regions, and that results in an optimal thermal or electrolytic diffusion. So, generally 3 driving forces are applicable in the spark plasma sintering: the pressure activated hard pressing, right. So, same pressure is used, so, and chemical activation by the addition of second phase through chemical reaction, and the physical activation by application of this current. So, in general the spark plasma sintering involves the simultaneous application of pressure and heat, that is similar to hot pressing, no difference. What is the difference here? The difference is because of the heating by Joule effect called resistance heating. So, the repeated application of an on and off DC pulse voltage to the powder compact leads to spark discharge at the particle and the particle interfaces or at the neck regions, and the Joule heating is accomplished. The spark discharges cause high temperatures between the particle contacts and voids. So, because of this such a high temperatures at the contact, there happens the easy necking. So, the necking is easy because of this spark, right, and then plasma. So, this is a schematic representation of the SPS technique. So, this is a generator of the DC pulse, and you can see this pulse current is being applied from one electrode to the other electrode. Here these are nothing but the punches. So, the electric current, the pulse current goes through this punch, the die and to the punch, right, and if the material has a good conductivity, then the current also passes through this material as well. So, because of this there happens a particle to particle, there happens the Joule heating, and this Joule heating results into high temperatures, and the diffusion happens very fast. You do not require higher temperatures for the sintering. Generally high heating rates up to 600 Kelvin per minute are possible in this SPS technique, and the sintering temperatures are lowered by 200 to 300 Celsius, and the holding time is only 5 minutes, right. So, the total processing time of heating and holding and then cooling, this is almost like 20 to 30 minutes time, right. The temperatures are reached at a very faster rates, heating rates of around 600 Kelvin per minute, right, and sintering temperatures are lowered by 200 to 300 Celsius, and the holding time is also 0 to 5 minutes. So, in some cases you do not need to even hold, just going to the peak temperature and then immediately decrease the temperature, cool it. So, the total processing time is reduced to a larger extent. Now, compared to the conventional pressureless sintering, the heating rates or the cooling rates in conventional pressureless sintering are very much low, right, as I told, less than 10 degrees Celsius per minute. So, heating to a temperature, high temperatures of 1500 or so, it requires several hours, right, and then holding is also of several hours, like 2 hours, 3 hours, and then again cooling with such a slow heating rates. So, the total processing time for a conventional pressureless sintering is like a 20 to 22 hours, right. In a hot pressing, so you can still go at a relatively faster heating rates, 50 degrees Celsius per minute. The required temperature also lower. So, once you go to the peak temperature, hold it for several hours and come back. So, generally speaking, the hot pressing processing time is like 10 to 15 hours. Now, you compare with this one processing time with this time of 20 to 30 minutes. So, you will have such a benefit if you use the spark plasma sintering, and this is one example to show the tungsten carbide 6% zirconium oxide ceramic powder mixture was sintered by spark plasma sintering method. So, you see the density of almost 100% relative density is achieved for the sintering at around 1300 Celsius. So, just for the comparison, the conventional pressureless sintering, the same powder mixture required 1700 Celsius, right. So, you have like 400 degrees Celsius lower temperatures needed for the sintering to 100% densification in spark plasma sintering compared to conventional pressureless sintering. So, and we will see more about the spark plasma sintering when we see certain case studies, and then one more important point in spark plasma sintering are because of the faster heating rates, the grain growth is also restricted. So, because of the faster growth, actually there is a relation called this G. If you see the grain growth at a particular temperature, there is a grain size initially, and there happens a heating rate, and if you see the temperature difference, right, temperature difference. So, there happens one activation energy required for the grain growth, that is Q, and then you have the Boltzmann's constant K and T, right. So, if you look at this relation, the grain size is larger if the heating rates are lower. In other words, in spark plasma sintering or microwave sintering, where few hundreds of Celsius per minute heating rates are possible. So, faster the heating, lesser is the grain growth. So, these type of techniques are used for restricting the grain growth, and we will see in other lecture where these type of sintering techniques are used to prepare a ceramic with a nanocrystalline material. For nanocrystalline ceramic preparation, you require such a faster heating rates. We will see in certain case studies in other lectures the use of such techniques of the spark plasma sintering, microwave sintering, where heating rates of more than 100 Celsius per minute can be possible. So, the use of such a advanced sintering techniques will result into a ceramic of a restricted grain growth. The grain growth can be restricted even to a nano size range if you start with a small powder particle size of nano, right. So, particularly for the nano ceramic materials or nano ceramic composites, these advanced sintering techniques with a faster heating rates are much useful. We will see in other classes how these are useful. Okay. So, summarizing today's class, we understood the processing of ceramics is different than the processing of other materials like metals. This difference is mainly because of their high temperature stability. The high temperature stability makes it difficult to use conventional routes of fabrication. Mostly ceramic components are manufactured by powder processing. So, in which the powder synthesis, their mixing and compaction and sintering. So, these three are the major steps in the powder processing. So, we have seen the principle and the limitation of ball milling, which is a mechanical synthesis of powders and for the mixing also, and then compaction of this powder, cold pressing, then the sintering. We have learnt important points of pressureless sintering, hot pressing and spark plasma sintering, and these the later techniques are called advanced sintering techniques. These techniques are generally used to prepare a dense ceramic with restricted grain growth, and we will see this in the other class. Thank you.